Good morning, everyone. I'm going to be describing the technology of pulsating heat pipes this morning and how they're being pursued in the cryogenic regime. They can provide a very key functionality for applications on the moon because they're a very effective thermal spreader. You can probably think of a couple applications where that would be useful. I'll be focusing just on the application for high-temperature superconducting coils this morning. And the work I'm presenting is a scoping study, you could say, and it's done in conjunction with my colleague, Professor Franklin Miller, and our graduate student, Diego Fonseca. We're all in the Department of Mechanical Engineering at the University of Wisconsin in Madison. Where I'm headed in the talk, you can see here, I want to describe some of the fundamentals of how pulsating heat pipes work and explain their properties in the cryogenic regime, and then also transition to tell you about how they are expected to perform in reduced gravity, and then transition to that application of the pulsating heat pipe for operating high-temperature superconducting coils. I'll end up by addressing the design challenge in the conclusions that I present. So, beginning with the fundamentals about pulsating heat pipes, a little bit of history. They were introduced in the heat pipe community in the middle 1990s, and I can say that since that time there's been ongoing development for room temperature applications, cooling electronics primarily. But it's only been since about 2008 that people have begun investigating the use of cryogens as the fluids inside of the pulsating heat pipes and therefore operating them in the cryogenic regime. Pulsating heat pipes, like heat pipes in general, have this unique feature that they have an amazingly high thermal transport capability. The pulsating heat pipe, though, allows one to have a very simple, lightweight construction. It's just a simple tube. There's no wicking structure inside, and the tube goes back and forth between the hot and cold regions. If you have enough loops back and forth between the hot and cold region, then this pulsating heat pipe can also be very orientation insensitive. That is, its performance can be. And so in that way, it's different than the conventional heat pipe. You can see here that the idea is that you take a simple tube and it's filled with some fluid, but you want the diameter of the tube to be small enough so that the surface tension forces dominate over the gravity forces. And what you end up with then, as you partially fill the tube, is a sequence of liquid, slugs, and vapor plug regions. What we mean by a small diameter is defined here. You'd like to have the diameter less than the square root of the ratio of the surface tension divided by the gravity times density difference between the liquid and vapor phases. So you take a tube with with that diameter, and you run it between a place where you're picking up heat, we would call that the evaporator end, down to the place where you're rejecting heat, call that the condenser end, and you loop it back and forth multiple times. The result is that, as you can imagine, in the warm region, you're increasing the vapor pressure of the fluid, and in the cold region, you're decreasing the vapor pressure of the fluid, and so there would be naturally a pressure imbalance wanting to move the fluid from the hot to the cold end. But because you have multiple loops, you have this competing factors in adjacent loops. And so what happens as a result of these many competing factors is that when you get enough heat or enough temperature difference, the fluid spontaneously moves very rapidly back and forth between the evaporator and the condenser ends. Sometimes you could say that it's oscillatory. In many cases, you would describe it as chaotic. But in either case, the fluid very effectively carries heat, both by sensible heat and latent heat, from the evaporator to the condenser ends of the pulsating heat pipe. There are a number of factors that we can identify that influence the performance of the pulsating heat pipe. I've listed here a number of fluid parameters, like the surface tension, the densities, the shape of the saturation curve. H sub F, G is the latent heat, and you'd have the specific heat of the two different phases, the viscosity of the two different phases, and the Prandtl number of the two different phases. So all of those fluid parameters influence the performance. In addition, there are a number of geometry parameters that are crucial, as we mentioned already, the diameter, but the lengths, for example, in the evaporator end or in the condenser region and in the region in between, we call it the adiabatic region. The number of turns certainly influences the performance, as well as the tube shape. Is it circular or square in cross-section or triangular? And then there are a number of different configuration variations that people have investigated. The fill ratio, that is, what percentage is full of liquid versus vapor, influences the performance. And as I mentioned before, if you have a small number of turns, then the orientation with respect to gravity has some influence on its heat-carrying capability. And as I mentioned also before, there is a critical heat flow that we've been able to identify, or a temperature difference that also turns on the pulsating heat pipe. If you're on the Earth, and you see here you've got 9.81 meter per second acceleration of gravity, here are the various diameters that define the maximum diameter you would use with a variety of cryogenic fluids. And what I want you to notice is that the diameters are on the order of 1 to 3 millimeters. So it's a very small, you could almost say capillary-sized tubing going back and forth between the hot and cold regions. And you can see the temperature ranges that you would have available with those different fluids. Next, I would like you to take a look at how that translates if you are on the moon. And again, I included 3 cryogens here, hydrogen, neon, and oxygen. And the main point that I want to notice here is that although the moon at poles has temperatures below 40 Kelvin, for reasons I'll show in a minute, I think you're likely to end up operating more in the temperature range between 50 Kelvin, and if you're going to use liquid oxygen, the lower range would be 55 Kelvin, or 54, where its triple point is. The upper region of where you would use oxygen may be more dictated by the current carrying capacity of the high temperature superconducting coils. And there you might get up to around 80 Kelvin before you're getting too warm. The pulsating heat pipes, as I mentioned, have been investigated in the cryogenic regimes with these various cryogens since about 2008. And I show you here some of the large effective thermal conductivities that have been measured, both by the Japanese group, the National Institute for Fusion Science in Tokyo, Japan, and some of our own data from just about a year ago using liquid helium. What you should notice is that the thermal conductivities are large, ranging, you can see, from 5,000 up to as much as 20,000 watts per meter Kelvin. And if you take a look at the graph in the lower right-hand corner on this slide, you'll compare that to the thermal conductivity of high-purity coppers. And there you can, even for RR100 copper, the best you can do, around 20 Kelvin, is about 2,500 watts per meter Kelvin. At 4 Kelvin, it's lower. If you're up around 50 Kelvin to 60 Kelvin range, again, you're limited to about 1,000 watts per meter Kelvin. So if you're using a pulsating heat pipe instead, you can easily exceed that thermal conductivity by a factor of 5 or more. So it's very effective thermal transport mechanism. The data on the lower left is from the group in Japan, and there you can see some of the orientation dependence. They were using neon in that graph, and the number of turns, I think, was around 4 or 5. So you need to have much more turns than that in order to avoid that gravity orientation effect. There are some correlations that have been developed, both with room temperature fluids and with cryogenic fluids, and you can see they're similar. And these correlations relate the heat carrying capacity. This is the large Q dot on the left-hand side of the equation with a variety of dimensionless fluid parameters. There's the Kármán number, Prandtl number, the Jacob number, and then N represents the number of loops back and forth. Beta is the orientation angle, and so you can see that we have enough data gathered so we have correlations for how these things depend. And if you carry through in the fluid parameters to extract how the heat carrying capacity depends on the acceleration of gravity, you can see that it's roughly inversely linearly related to the gravity. Therefore, with the 1/6 gravity on Moon compared to Earth's gravity, you can expect that the heat carrying capacity of these devices will be about 6 times larger than on the Moon, or on the Earth. So very high effective thermal conductivity, very effective as a thermal spreader. This is some data showing you that back in 2004, some parabolic flight experiments confirmed that expected behavior. And when the acceleration due to gravity was low, near zero, that was the region at the time when the temperature difference between the heated region and the cooled region was at its smallest, and therefore the effective thermal conductivity was largest. So this is a known feature of these devices. This slide shows you some ideas that we have for our own parabolic study with nitrogen-based pulsating heat pipe, and should be doing that within the next couple of years. Superconducting magnets have a very strong temperature dependence to their current carrying capacity, and this graph shows you the field dependence of that current carrying capacity as a function of temperature. It happens to be for what we call a type 1 superconductor, BISCO 2223 sample, but the shape is the same as what you would get today with second generation YBCO tape style high temperature superconductors. The point is here, if you want to be able to get higher fields, you really need to pay attention to what temperature you're operating at. And so lower temperatures give you higher current carrying capacity, which then in turn translates to smaller cross-section of the conductor and a lighter magnet in general. High-temperature superconductor magnets allow us to run in a little bit more relaxed way than we run low-temperature superconducting magnets, and that is that if they transition into their non-superconducting state, the operation is still possible, and it becomes more of a thermal management problem. Can you take away the heat that's being generated sufficiently to keep the magnet operating, rather than having a thermal runaway quench scenario that you get with low-temperature superconductors. So, in high-temperature superconductors, because you will have joints and AC losses if you're operating on an AC circuit, or even, for whatever reason you go above the superconducting plane and you're generating some heat, then you want to take away that heat, and you won't have atmospheric conditions to convect the heat away. You're going to need to radiate them away. But as you transfer that heat to a radiator and reject it from the radiator also will increase its surface temperature compared to the surrounding temperatures. So if I run this little animation on the screen and representing an increased heat flow, you see that the relative temperatures of the HTS coil and the radiator also increase compared to the surroundings. So the message is that you want to use the PHP to keep the delta T between the coil and the radiator small, and you want your radiator large enough so that you can keep its temperature close to the ambient temperature. We did some calculations here that showed that depending on which ambient conditions you imagine that you have, 40 Kelvin, 50 Kelvin, 30 Kelvin, or whatever, you can calculate what the temperature of your radiator surface will be as a function of how much heat you're trying to reject. Very simple calculation, but it shows that if you want to be transferring something on the order of 1 watt of heat, you may need to be allowing a couple of square meters of radiator surface in order to keep your magnet at 50 Kelvin or below. And so the implications are you run the PHP to minimize the temperature difference between the coil and the radiator, and then you try to make your radiator large. And it turns out that one way or another you're going to have to do an optimization study to keep the overall mass of your system low, because if you wanted a lower temperature, you could make your coil lower, but it would make your radiator panel larger. And in general, for the temperatures that we envision, it looks like oxygen is probably the best fluid for the PHP. So, in summary, the lunar pulsating heat pipe provides this key mechanism for passive cooling thermal spreader. It's simple. The construction is lightweight. Probably be about 6 millimeters for oxygen. It gives you very high effective thermal conductivity, and because it's such a simple geometry, it can be easily integrated into superconducting coils. Over the next 5 years, there are a number of parametric studies that we want to do with cryogens, taking a look at the lengths of the various sections of the PHP and how you might best integrate it with coils. And then, as I mentioned, there's going to be a system optimization study to minimize the overall mass for the overall system. But I think I'll stop here and give some time for questions. Thanks very much for listening.